Okay, welcome to note set number 22. I had a little bit of a delay here over the past several days when Explain Everything seemed to just stop working. I couldn't import anything, I couldn't get it to work, but now I think I have it behaving. Anyway, sorry for the little bit of delay here. Hopefully you didn't get too far behind waiting for these to show up online. Anyway, we're going to move into how we actually use the DFT for practical spectral analysis of signals. We've seen how to use the DFT for making FIR filter implementation work very efficiently, but now we're going to see really the real power of the DFT for doing all sorts of interesting things, analyzing the spectrum of signals. So my presentation is primarily based upon Chapter 6 of Peratt's book, which I've put Chapter 6 up on Blackboard, but also portions of Section 7.4 of Proachus and Montelakis. So here's the basic idea. We take some continuous time signal in through like a microphone or a antenna or something like that. We run it through some front end processing. If it's an RF signal coming through an antenna, we do some down sampling or down shifting, frequency shifting down with a mixer, run it through an A to D converter, or we use the A to D converter in a kind of a bandpass sampling mode, and we get samples of that signal, and we want to then look to see what is the spectral content of this signal. And in particular, we're trying to identify spikes. A lot of signals contain some sort of sinusoidal signal, sinusoidal component, and we'd like to estimate the, detect the presence of that sinusoid and estimate its frequency. Or just look at the spectrum, identify some characteristic of the spectrum, usually things like spikes and things like that. So the challenges in this are that the available samples that we have might only be a small number. We might only be able to observe this signal for a very short period of time. So like a radar may only be spewing out its signal for a very short blip, and that's all we get to intercept. But also, if the signal is long, the spectral content might actually be time varying. So the spectrum of music changes with time, obviously, as the music is being played. And so we may want to do our spectrum analysis on a block-by-block basis. And the shorter we can keep those blocks, the better we can focus in on a short period of time where the spectrum might be fairly static or stationary. So there's many reasons why we want to be able to do the best job we can with a small amount of data. But the problem is, we'll see as we try to keep the record length shorter and shorter, that will cause a loss of resolution and accuracy. So the real challenge of practical spectral analysis is to try to do the best job you can with as little data as possible. And so that's what we want to kind of look at. And we will focus largely on this kind of sinusoidal aspect. If you can learn how to deal with detecting and processing pure sinusoids, you'll have a good feeling for any other kind of signal that you might want to deal with. Okay, charging on here. Let's look at an example here. This comes from the realm of electronic warfare, where I spent about 8 years working in an electronic warfare group prior to coming to Binghamton University. So this is the kind of stuff that I used to do on a day-to-day basis. So we would, intercept t seconds, and t is usually pretty small. We're talking like, tens of milliseconds, maybe at most, 100, couple hundreds of milliseconds of a radar pulse train. And I'm showing that pulse train here. Very simplistic case, just some pulses with modulating a sinusoid. And the PRI is called the pulse repetition interval. So that's the spacing from the start of one pulse to the start of the next pulse. I don't show it here, but just for completeness, the width of the pulse is surprisingly called the pulse width. So, so we have these things here, and that will allow us to well, now I can't get that to go away. There we go. Let's try to get that to go away. All right, there we go. So since this is a periodic signal, we can express it in a Fourier series. And the period is the PRI. And so the fundamental frequency will be 1 over the PRI, and then the modulation, we're assuming that there's no other like phase modulation or frequency modulation on this. So the carrier here will cause that shift up by FC. And the C sub n are our Fourier series coefficients. And so if we didn't have the FC, we would have this Fourier series spectrum centered at the origin. But because we have the carrier on there, it moves that spectrum up to be centered at FC, and we would have something also down at negative FC, which I don't show here. And the spacing between these harmonic spikes is the 1 over PRI. So that's the fundamental frequency of the underlying periodic pulse stream. So, so that's the theoretical spectrum of this pulse train. If it continued on like this forever, and if we think about this in terms of a continuous time Fourier transform, it would look like this, with these spikes representing delta functions for each of the sinusoids. So we have a bunch of sinusoids. Each one of those sinusoids Fourier transforms into a delta function. And then if we think about the DTFT of the infinite duration signal, we would also end up with delta functions. So that would be we could think about this kind of shape here after it's been shifted back down to some low enough frequency where all of this would be fitting into an appropriate minus pi to plus pi, and we would still have the delta functions. And then when we collect some number of samples, we've seen that these delta functions will get smeared into lobes, and that's what we're showing here. And we'll talk more about how this all works in just a little bit, but we've already seen a little bit of that. And so the issue is we want to make sure maybe that we can separate these different spikes. If we can do that, we might be able to tell something about the particular characteristic of that particular radar. We might be able to identify this is a particular type of radar by looking at the relative heights of those things. So, aside from the specifics of electronic warfare, this is an interesting problem. How do we make sure that we process all of this to try to see the best version of this that we can, but we know that it's going to be smeared. So let's look at some of the details of this. And the big thing that we're going to be looking at, we've talked about the rectangular windowing. We're going to delve more into window functions and what their impact is and why we use them. And so this is being covered in the section 6.1 and 6.2 of the chapter 6 of Peratt's book that is on Blackboard. Okay, so moving on here. So here's the basic idea. We've got some underlying signal that we're going to collect just a finite amount of data. So for here, we're going to be calling y of n the infinite duration signal, and x of n will be the effectively windowed version of that. So we model the conversion of that into a finite number of samples by imagining that the samples that we don't collect are set to 0. And so x of n is the finite duration signal that we have available, and we model this process of collecting some finite number of non-zero samples by taking y of n and multiplying it by a rectangular window, w sub r of n, where w sub r of n is just 1 in the region where we're collecting, and it's 0 elsewhere. So this is just math. What we physically do is we just collect n samples. But to be able to analyze this mathematically, what we do is think about our original infinite duration signal y being multiplied by a rectangular window, and that's mathematically modeling the act of collecting n samples. Okay, so once we do that, our available data x is related to the unavailable signal y of n through multiplication, and we have a multiplication theorem for the DTFT. I tell you the equation here in Peratt's book, but you don't have that chapter, but we've already talked about the multiplication theorem for the DTFT. So multiplication in the time domain corresponds to convolution in the frequency domain, and because the DTFT is periodic, it's really a circular convolution. So that's what I'm indicating here with that symbol. And you'll notice this notation. Peratt is a stickler for precision, and that's really why I like the book. So what we're saying is we're not putting an argument on the function. We're just saying take the entire DTFT of y, take the entire DTFT of the window function, convolve them, and then you evaluate that at the point theta. So that's just actually a more precise way of representing this information than what you normally see in a textbook. And it's really no different. It's just this equation right here. So, don't get hung up on that new notation. So we're just doing this convolution here. We're rewriting each in terms of this function lambda, and we're flipping and shifting. Now, technically, this should be really done the other way around with theta minus lambda, but the DTFT of this has some symmetry, so it doesn't really matter. But the important thing is that is the action that causes the smearing or the leakage or the smoothing. So the DTFT that we can see is a smeared version of the DTFT that we really want to see. And to just get an idea of what this window function looks like in the frequency domain, we've been down this road already, but let's do this again. We have the DTFT of the window function. It's just one values from n equals 0 out to capital N minus 1, and we're just taking the DTFT of that. We immediately get this result by taking advantage of the geometric sum. Then we do some algebra, and the purpose of pulling these things out in front is to just get ourselves into an Euler's form, and we end up with this sine theta n over 2 over sine theta over 2. And Peratt gives a name to that part of it. There's this phase term out in front that isn't the most interesting part. It's really the sine over the sine part, and Peratt calls that the Dirichlet kernel, so named after a famous mathematician named Dirichlet. So this thing looks sync-like. It's not exactly like a sync, but it's sync-ish, or sync-esque, or sync-like. So that's what we got. And so there's a plot of it, just the Dirichlet kernel part without the phase part. And so that's real, so we can just plot it versus theta. And I've played my favorite trick here, theta divided by pi. So when we're out at 1 here, that's pi, that's minus pi, 2 pi minus 2 pi. So we can see that this thing does indeed follow the rules of periodic DTFT. And what we're showing here is that as we let n get larger, we see a couple things. We've got this main lobe, and we'll see what the behaviors are or what the impacts of main lobes and side lobes are. And then we've got all these other things out here which are the side lobes. And we can see that as we go from n equal to 11 out to n equal to 41, what ends up happening? The main lobe gets narrower, and the side lobes look like they go down, but in reality, we'll see that this largest peak, which actually is shown here as the negative, and soon we'll be looking at these things in dB, so those negative peaks will get flipped up. And so the maximum peak is actually the first one, which goes negative here. We'll show that that is 13 dB down relative to the main lobe peak, regardless of n. So increasing n doesn't reduce the size of that first peak, but it does kind of reduce what goes on further out. So there is some advantage there. And we'll look at some pictures of these. It's better to look at it in terms of dB. But the basic idea is that as n goes to infinity, this thing will converge in some sense to something that's delta-like. And in fact, if we analyze this inside an integral and let n go to infinity, it will behave just like a delta function as we let n go to infinity. And remember that this is the thing that's showing up inside a convolution integral, and as this thing goes to more and more delta-like, it does less and less smearing / leakage. So remember, smearing and leakage are the same thing. The more historical term is leakage, and the term that I prefer, I don't know if I made it up or I heard it from somewhere else, but I call it smearing, because that's really what it does. We also know that this main lobe width, measured from the point where it crosses 0 to the point where it crosses 0, is 4 pi over n. So as n goes up, the main lobe width gets narrower, and the height of it gets bigger as well. So all of these things tell us that as n gets bigger, we'll have less and less smearing from this Dirichlet kernel. So let's take a look at the impact of this on our processing. Just as a way of illustrating, and we'll see some other illustrations of this, suppose our underlying DTFT is a rectangle. So that means our it doesn't really matter, but it means that our time domain signal was a sinc function. So we collect some finite amount of that sinc function, and we're going to compute we're going to look at the DTFT of this. And so if we wanted to compute, say, the point at, say, pi over 2, we would take the Dirichlet kernel and we would shift it by pi over 2. So here it is shifted. We would then do the product of our true with the shifted Dirichlet, and we would get something that looks like this. And then to to do the convolution, we would integrate from minus pi to pi. So we would integrate and we would be finding the integral of that thing, and we'd get some number. And that would be the number that we would end up, and we would plot that there. And then for various shifts of this thing back and forth, doing this process over would tell us how to get the different numbers here. So if we wanted to find out what this thing looked like out at, say, 3 pi over 4, out where the true DTFT, let me just switch here and get rid of this here a different way because that's taking too long. So if we wanted to find out what the finite duration signals look like, DTFT looked like, say, out at 3 pi over 4, we would shift this over just a little bit more, and we would, only get, say, part of this big thing here, but we would still end up integrating that and getting some non-zero value, and we can see that non-zero value shows up out there. And so you can see as you slide this thing to get the different frequency values down here, these ups and downs are going to result in these ups and downs. And then as we slide it back and forth here, we'll see ups and downs there, and as we slide this main lobe past this edge, that's what accounts for that falling off. So we see a lot of things going on here, and mainly what we're seeing is that the main lobe width is responsible for how fast that drops off. So a narrower main lobe will give us a faster drop off there, which will show this instantaneous drop off better. And it's the side lobes that result in this up and down smoothing or smearing. So we can, if we understand how this works, we can kind of get a feeling for how it will work in general. And we can also see, and this is the important thing, we can see what the different behaviors are due to the main lobe and the side lobe. So a good way to study this phenomenon and the impact of main lobes and side lobes is to look at what happens when I'm trying to do a spectral analysis on two complex sinusoids. So we make them complex just so that we only have a positive frequency to worry about and we don't have any negative frequency side to worry about. It just simplifies things a little bit. So for each term we just have so for this we just have one spike, and for this we just have one spike. And obviously I'm showing here the things outside the minus pi to pi. That's why we have all those other spikes out there. Those are the spikes for the 2 pi periodic spectral replica parts of this. So so this is our time domain signal here, and here is the DTFT of the infinite duration signal. So we see we get a delta at theta 1 and a delta at theta 2. And then our theory says that we take this spectrum and convolve it with the spectrum, circularly convolve it with the spectrum of the window DTFT. So here's the window DTFT, here's our theoretical spectrum, and we're going to do a circular convolution here. I guess I don't really need that N there. We're doing a circular convolution, and we know from our theory that whenever we convolve anything with a delta function that's been shifted, we end up with a shifted version of the function that's being convolved with the delta function. So that's a ramification of the sifting property applied to convolution. So what's going to end up happening is that we end up with this delta function taking our Dirichlet kernel, and that's the only thing that I'm showing here. I'm leaving off the phase part of it, but it takes the Dirichlet kernel and centers it at wherever the delta function is, and then the other sinusoid centers another version of the Dirichlet kernel out there. Now, I will point out that technically these are delta functions, in this plot for y. And so technically the delta function goes to infinity. And so you may be wondering why I'm showing different heights here. We use that graphically to illustrate that A1 and A2 have different levels. So here we're looking at two sinusoids where one is strong. So say A1 is bigger than A2. And when those things get convolved with the Dirichlet, we'll literally have different heights. Even though these are infinitely high, they have a different area, and that area gets conveyed to the height of the shifted Dirichlet kernel. So that all works out in the math. You can see that the A1 ends up out in front of the Dirichlet kernel out there. So this is very insightful. If we look at this, we can really make some really good insights into how things are going to work. So if we were to process this signal, a finite number of samples, we would get not these delta functions that we really want to get added together. We would get two Dirichlet kernels added together. And down here I'm showing those two kernels separately, but in reality we don't get them separately. We get them added together, right? So you would really have to add the red and the blue together. And if you look here, you can see that there's going to be some cancellation between the downward lobe of the blue one and the upward lobe of the red one. And because the red one is weak, here we are assuming that A1 is much greater than A2. So its main lobe is on the order of the height of the side lobes of the blue one. And so side lobes of the blue one can actually cancel and obliterate the main lobe of the red one. And so we may not actually be able to see it at all. So this is what's known as side lobe leakage, or side lobe interference is what I would actually prefer to call it. I never like what anybody else calls things, I guess. And so this is where the side lobes of a large sinusoidal component will obscure the main lobe of a small amplitude sinusoid. And so we might not even be able to observe the presence of that red one, and we'll see some examples of that as we go through this. So we're seeing some of the issues of side lobes, and we're observing here that what we really want to do is make side lobes as small as possible. If we could eliminate side lobes entirely, then we would have no problem seeing that little red main lobe pop up. But here we'll actually see, have a problem seeing. So here's another scenario. Now we've got two closely spaced sinusoids. So the theoretical DTFT would be two delta functions. And here I'm showing that their amplitudes are a little bit different, but they're similar in height. And so on this middle plot, we have the blue curve corresponds to the lower frequency, higher amplitude one. The red one corresponds to the slightly higher frequency one. But in reality, remember, we're getting the sum of the blue and the red. And, I just did this by hand in PowerPoint with PowerPoint's drawing capabilities. So I don't know that this is really how it would look when you add them together. But my artistic impression of this is this purple curve. And we can see that the two spikes that we can clearly see in the true theoretical DTFT if we look at the DTFT of the finite duration signal, just looks like one blob. We have the fact that the main lobe's width ends up being so wide that for these two closely spaced sinusoids, the two main lobes kind of lie on top of each other and fuse into one big blob. So the analogy I like to give is, hopefully you can envision this. If you wear glasses, imagine taking your glasses off. If you don't wear glasses, imagine putting somebody else's glasses on. So the people who just took them off to do this little thought experiment, those of you who have good eyesight, put theirs on. And now you're seeing everything all blurry. And if you were to look at a Christmas tree with two closely spaced little lights on the Christmas tree, one blue, one red, and they fused together into just one light because your vision is so bad, you'd see that as kind of a purple, one big blob of purple. And that's kind of what we're seeing down here. Now, obviously, in DTFTs, there's no colors. So I'm just using that as an illustration. So this is called main lobe smearing, or at least what I call it. So we've got a wide main lobe for when we have two closely spaced sinusoids and they smear together. So, we've illustrated these two effects with these two distinct sinusoids. But remember, this all happens even if our Y is some arbitrary DTFT, there will be smearing of closely spaced spiky features, and strong features in one frequency range will obliterate weaker characteristics in another frequency range through side lobe interference. So these are the two effects, and if you can visualize how they work, you can wrangle through thinking about a lot of different scenarios other than just complex sinusoids. So armed with that, let's think about what we're doing here. We've seen this before. You've seen it back in the 301 course on signals and systems. We've seen it before in this course as well. And that's because this is a great way to visualize what's really going on. So everything's happening right here. We've got our continuous time signal with some underlying CTFT, and then we've got sampling that happens as we go through the A to D converter. So if we imagine this discrete time signal being infinite in duration, that's why I have the sub-infinity here. So we've got that thing coming out of the A to D converter, and theoretically we're thinking about that. So remember, everything on the left-hand side here, these three yellow boxes on the left-hand side, are things that we don't do in an actual processor, but we think about them as we're thinking about designing and implementing that processor. So we've got the CTFT. After sampling, we may experience some aliasing, but we've still got nice sharp spikes because we've got infinitely many samples. But then we collect a finite number of samples, and we're still just thinking theoretically, hypothetically inside our heads, not something that we can really do. We collect n samples, and as soon as we do that, the underlying DTFT now is a smeared version of our sub-infinite, and that's why we have this sub-n here. So the truncated signals DTFT is a smeared version of what we really want to see, and you can see these spikes get smeared. That's main lobe smearing. Now I'm not really showing the effect of side lobe smearing here so much, but just overall there's going to be various smearings of both main lobe smearing and side lobe interference all grouped together. And then finally, however many samples we collect, we can only compute points on this DTFT, and that's what we show over here. So the dashed line is repeating the x sub n of omega, and the dots with the stems are showing a plot of the points that we actually compute with the DFT. So we've seen this before. Now we're starting to see a little bit more about what this smearing consists of. And this is, again, we've seen this before, just pointing out the various errors: aliasing error, smearing error, and grid error. We're focusing in this set of notes on smearing error. And we've already talked about how to control that through the choice of n. As we collect more data, the amount of smearing is reduced. But we're now going to focus on window choice. We don't have to just collect data as if we're using a rectangular window. We can taper this data. We can apply a window of any shape that we wish, and we'll see why we might want to do that. But keep in mind that really the only thing that we're actually doing here physically inside our system is we're collecting samples and we're computing a DFT. All of this stuff is what we use to interpret and understand why we get what we get and how to make sense of looking at the plot to see, does it make sense? Do we have obviously some errors that, that we should take care of? So let's take a look at a very simple example here. And we pick this example because not because it's something that we would necessarily find interesting to do in the real world, but because we can compute all the theoretical results precisely for this case. Whereas in the real world, we're going to be receiving some arbitrary radar signal or some music signal or something like that, and we don't have any nice theoretical results for those things. But if we pick as our continuous time signal a decaying exponential, b is greater than 0, and we have a negative b up there, so this thing does definitely decay, and b controls the decay rate. And that's a signal that shows up on our CTFT tables, and the discrete time version of it shows up on our DTFT tables, so we can figure out exactly what the spectra of these things look like. So suppose that B is just 2000 pi, and suppose we sample this signal at 30 kilohertz, so 30,000 samples per second. And suppose we just take 8 samples. So we're going to take 8 samples, not because that's something that we would really want to do in the real world, but rather because it's something that we can easily see our plots. So here's our 8 samples in the time domain. So it starts at n equal to 0. We have a value of 1. Because we would sample that at t equal to 0. And then if we figure out how far in time our first sample will be, we plug that value into here, and we would get something that's just a bit above 0.8. And so on, and so on. It decays down. Okay, so that's the signal that we're going to processing. So we're going to put these 8 samples into our computer. So we imagine they're coming out of this A to D converter, and we put 8 of them here in our memory array. And so now we can simulate actually doing this in MATLAB. So we've got these 8 samples that we can calculate the numbers for, and we can imagine this real world signal coming into our A to D converter, and MATLAB will give us these numbers to look like the things that would come out of the A to D converter and get stored in this memory array. Then we'll do some DFT processing on it, and we'll get some numbers over here. We'll get 8 numbers over there. But the other thing, the beautiful thing about this is that we can also theoretically figure out exactly what the CTFT of that signal looks like, what the DTFT of that signal looks like for infinitely many samples, as well as for just 8 samples. So we can compute all of those yellow boxes for this example and see how it all works together. So let's continue on. So here's the MATLAB code for this. I'm not going to go into explicit detail on this. But I would encourage you to study this. But I'll rip through some of this here. I'm setting my FS and I'm converting it into a sample spacing. I set up a time index, discrete time index, n equal to 0 out to 7 to correspond to the 8 samples. And then I compute the actual time instance corresponding to those 8 samples. I set my B value to what I want, and then I compute the 8 samples. And then I do a stem plot of that versus N, not versus T, just so that we can see how it looks. And then I do an FFT, no zero padding, and I do an FFT shift. And then I compute my frequency vector. We've talked in the past about how to compute that frequency vector. And usually you can plot your DFTs in a variety of different ways. You can plot them against the K values, which in my opinion, you rarely ever want to do that. You can plot them versus radians per sample, so that'll be between minus pi and pi. Or you can take that discrete time frequency and convert it into the equivalent continuous time frequencies, as long as you know what the sampling rate is. And we know what the sampling rate is, so we can map minus pi to fs minus fs over 2 and pi to fs over 2 and plot it that way. And so that's what I've done here. You can see that I've created a delta F, that's the spacing between my DFT points. It's just Fs over N, because my range is going to go from minus Fs over 2 to Fs over 2, so that's a distance of Fs, and I'm splitting it up into N bins. So my spacing between DFT points is Fs over N, and then I just create the right integers to multiply by those delta Fs to go from minus Fs over 2 to just shy of Fs over 2. And then I plot it. And I plot it as a stem plot. When you do real-world DFTs and you've got lots of points, you generally don't plot them as stem plots because it becomes a very busy and crowded slide with all those stems on there, so closely spaced. But with 8 points, it makes sense to show it as a stem plot. And so I've gone through this already in the MATLAB set of notes, but these are the two tried and true ways that I use to create my appropriate frequency vector. So if I want to plot versus radians per sample and go from minus pi to pi, this is the result I use. And if I want to plot in hertz and go from minus Fs over 2 up to just shy of plus Fs over 2, this is the result that I use. And I've used this so often, I don't even have to think about it. I can just type quickly, and that little expression just spews right out of me. And it would be great if you could get to that point too, because this is such a common thing that we do all the time. Okay, so we've got our continuous time signal. We've got 8 samples that go in here. We do our DFT processing. We get numbers out here, and we're going to do an FFT shift, and we're going to plot those things here versus hertz. And so this is going out to, you can see the times 10 to the 4th. That's because our sampling rate is 30,000. So we're going out to, that 17, by the way, is the page number, slide number. So we're going out to almost, well, down here we're at minus Fs over 2. So that's minus 1.5 times 10 to the 4th. So that's minus 15 kilohertz. If I'd been clever, I would have done this plot in terms of kilohertz, and you'd have seen negative 15 there and positive 15 up here. But alas, I was not clever when I made this. So what does this tell us? We see 8 points. Big deal. Does it make sense? Where are our errors? So let's explore this to try to understand how these points relate back to all the plots that we've been showing over here. The DTFT for the finite duration signal, the DTFT for the infinite duration signal, the CTFT for the continuous time signal. So let's take a look at all of those. So we're going to study each of these. We'll look at this thing, and we can, for this example, we can exactly compute that. That's what's beautiful about this example. So for this example, we know what that looks like, and we know what this looks like, and we'll know what that looks like. So we can compute those kind of offline, so to speak, and compare it to what we actually get here. And now I'm showing some zero padding, and we'll be able to interpret what the effect of the zero padding would have on all of this. Again, remember, the only thing that really happens inside your processor is x of t comes in, gets sampled, and we spew a finite number of samples into an array. We might, at least effectively tack on some zeros. We do DFT processing. We get a bunch of stuff. We'll do an FFT shift on that and plot it and look at it. That's all we can do. The rest is understanding based upon what we know about theory. Great, let's move on to the next page and see how we do all this. So we need to look at what does the CTFT look like for this signal. Well, here's our continuous time signal. We go to our trusty continuous time Fourier transform table, and we find out that that exponential looks like this in terms of omega. We replace omega by 2 pi f so that we can plot it versus f. And now we can write some MATLAB code to make a plot of this function, magnitude of it anyway, to see what it looks like. So we're computing the theoretical CTFT. Can't do this in the real world. We can only do this because we've picked a very special example to look at that we have on our table. So we set b equal to 2 pi times 1,000. And we're, I just picked a range. We're going to plot it from, well, I'm going to compute it from minus 200 kilohertz out to plus 200 kilohertz. But I've zoomed in on this. So I create a frequency axis that ranges over that whole range. And so that's all good. And then here is the equation that computes that. That's simple enough. And the next thing I'm going to do is plot that. I'm going to plot the magnitude of it. So I use my ABS command to plot that. And I do want to point out that I picked 100 here so that this curve would be nice and smooth. Remember, this is 10 kilohertz here, so I've got thousands and thousands of points out to there. I'm going every 100 hertz all the way out to 10,000. So I got lots of points, and they're very closely spaced, and I get a nice smooth curve. The dashes here are because of the plot line type that I used. So notice that you can put the line type right into a plot command. So that's very, very nice. So you should get used to doing that. The R makes it red. The dash makes it a dashed curve. And so I plot that. And after I plotted this, I probably realized that, whoa, this was too big of a range to plot. Everything was all squished in, and so I zoomed into looks like minus 45 to plus 45. So I just zoomed it. I just probably did that by hand pretty much. Or there's a command called axis that you can use. So you say axis, and then you put 4 numbers in here. The first one is the leftmost x value. The second one is the rightmost x value. The third one is the bottom y value. And the fourth one is the top y value. So you can set the 4 corners of your plot. And so that's a nice command to use, is the axis command. Okay, so we've got this nice plot here, and so that's our CTFT, courtesy of theory and Fourier transform table. So let's proceed on. Our next plot that we want to find is the DTFT of the infinite duration samples of this. So, so we place our nice, we place our nice CTFT plot right up where we've been putting that CTFT plot. So there it is. And so now we're going to take and look at the samples of this and imagine that we have all infinitely many of those and what we get. So let's look at the DTFT of the signal at the ADC output and imagine that we have it forever. So we've got our sample, our signal x of t. We're sampling it at a rate of fs samples per second. So we're just simply evaluating x of t at the points, capital little n times capital T. And so we plug that in for our signal here. And we see that we can combine the e, the minus b, and the t using properties of exponentials. We can write that as e to the minus bt, whole thing raised to the capital N. And so we can now define an a, where a is this thing that's in the parentheses here, e to the minus bt. And because of the way that we set it up, with a negative, with b set equal to a positive number and then with a negative included in there, the magnitude of a will be less than 1. In fact, for our case, a is positive and less than 1. So we'll have a discrete time signal. That's our discrete time signal, and we know what a equals. So a is equal to e to the minus bt, so we can calculate that. And we look at this signal and we go, I know what that is. I've seen that before, and I've got that on my DTFT table. So I go and I look it up on the table, and there it is. And so that's my x sub infinity. That's my DTFT sub infinity result, and this is still theory. We can only do this because we're doing a nice textbook signal, and we're doing that so that we can see all of these things from a real example, not something drawn with PowerPoint. So we've got this thing, and we want to compare that to the CTFT. Now remember, the only error that we'll be seeing now will be the aliasing error. And if we go back and we look at that CTFT's Fourier transform, we see that it never goes to 0. It swoops down, it gets smaller and smaller and smaller, but there will be some aliasing. No matter how fast you sample this thing, it's certainly not a truly band-limited signal. So there will be some aliasing. And so let's take a look at that on the slide. So here is the code to compute and plot this result that came from our DTFT table. So just for convenience, we define capital T as 1 over Fs. So that's just for the purpose of properly computing our A. So here's our A computed to be e to the minus b times t, so that's why we calculated the t. And now we're going to go from minus 3 pi up to 3 pi, and I picked a spacing of 0.01. I just arbitrarily picked that, and it turned out to be appropriately fine grid. I could have made it 0.001, but if I'd made it 0.1, I probably would get a jagged, more jagged looking curve, and I don't want that. I want a nice smooth curve. So I picked a fine enough grid on which to evaluate this function. And so now here is the equation. This is literally just MATLAB for that. So I've got one dot divide. Remember, the dot says divide element by element, and since omega is a vector, the thing down in the denominator will be a vector. So I need to do one dot divide to divide element by element. So that literally just computes that function. So I've evaluated that at every one of these omega points from minus 3 pi out to plus 3 pi at a spacing of 0.01. Now, notice that I can go as far as I want because I'm not doing a DFT. I'm literally just evaluating a function. So I could go from minus 10 pi to plus 10 pi if I want. So there's none of this minus pi to just shy of pi like we have with a DFT because we're not computing with a DFT. We're computing a function, an expression that we're evaluating at whatever points we want. Okay, so we've done that, and then our next line here is just a plot of that thing, and I'll explain why I multiply by a capital T there when we look at the results in just a bit. And I put some nice labels on. I do a hold on, and then I do on top of that I plot my CTFT, and notice that I'm dividing my f by fs over 2. So that also gets me to the same normalized radian frequency. So when I normalize this, minus pi becomes minus 1. And when I normalize this by fs over 2, negative fs over 2, which corresponds to minus pi, also ends up getting normalized to negative 1. So the purpose of dividing by fs over 2 here is to put this plot on the same equivalent frequency axis as that one. Now I could have done it the other way. I could have plotted this thing relative to physical frequency and had it go from minus fs over 2 up to fs over 2 and then put this one on top of that on that same axis. But I didn't. I put it in terms of the normalized discrete time frequency because we're looking at the DTFT plot. That's our focus here. Okay. This command axis X, if I think of it, I'll post that up onto Blackboard. It's my modified version of the axis command because I found that more often than not I only want to change one of the axes. So I wanted to zoom in to minus 3 to 3. Remember this F frequency from before that's carrying over from our previous slides, that went way out. Remember, I went from minus 200K out to 200K. So that thing extends very far. And so I'm just kind of zooming in to the minus 3 to 3 to correspond to the minus 3 pi to 3 pi. If I think of it, I'll post the axis X on Blackboard. If I forget, just email me and I'll send it to you. It's not a hard command to trump up yourself. Now, I will state in passing, why am I saying H equals plot? Well, I don't use it here, but that's called a handle, a graphics handle. Once I assign H some number that comes out of this plot command, it's an identifier number that will that identifies that particular curve. And then I can then go back and use that H number to set any characteristics of that curve I want. So suppose I wanted to change the line size, the line width of it, I could do that later. With code, not manually clicking on it and changing it. So it's a nice feature when you're trying to write code and you know I'm going to want this to be a certain characteristic, and you can set it right in your code. Okay, so that just computes and plots that function, and it plots the magnitude of it. And I'll explain why we multiply by capital T. So here's the result of that. And you can see the different axes laid on top of each other. So the minus pi to pi corresponds to the minus fs over 2 to fs over 2. And I've set these things up so that I mapped the CTFT onto the normalized radian per sample axis. So my minus pi is divided by pi, my pi is divided by pi, so that's the minus 1 to 1. But we can always, once we've got this normalized, remember minus 1 corresponds to fs over 2, minus fs over 2. Let me do it on the positive side. 1 corresponds to fs over 2. 2 corresponds to 2 fs over 2, or fs. So once I have this normalized radians per sample axis, it's very easy to just in my mind reinterpret it as either of these two axes that I want. I want to think about discrete time. 1 is pi. I want to think about the continuous time frequency axis. 1 is fs over 2, which is 15 kilohertz. So I love doing this normalized frequency axis this way. It makes it so easy to think about. Now, what's with the t? Why did I put a capital T here multiplied by my DTFT? Well, remember, our theory, our sampling theory, says that the DTFT infinity ends up being all of these spectral replicas of the CTFT with a 1 over T out in front. So I'm trying to compare this thing to the original CTFT up here. But there's this 1 over T that's making their heights difficult to compare. So I multiply this by 1 over T to get rid of that, and now I can compare them they'll be the same height, essentially, is what I'm saying. So I'm effectively normalizing both the horizontal axis as well as the vertical axis. It's taken me years to come up with all these little tricks, but they're very, very handy. So that's why we do that. So I'm plotting T times the DTFT to undo this 1 over T here so that I can compare my plot. If I didn't do that, the red and the blue curves up at the top would have vastly different heights. But by doing that, I can compare them and see. So what am I seeing here? Well, I've got my CTFT plotted on top of the DTFT, and I've got horizontal and vertical axes managed so that everything can be nicely compared. In theory, with a perfectly band-limited signal, with sampling done perfectly, these two curves should lie on top of each other, perfectly on top of each other. But we're not seeing that. We're seeing the effect of some aliasing. So we're seeing that the DTFT is a little bit above the CTFT there, and that's due to aliasing. So remember, there's going to be another version of this red one that corresponds to this one, and it'll come down, and that tail adds to the other red curve and adds together to create the blue one. So those are these terms down here, each shifted by, 2 pi over, k2 pi down here, but that's really shifted by 2 on my normalized axis. I also see aliasing effect there, right? This tail is coming all the way down here, and there's still a little bit enough there to make that peak go up. Remember, there's another tail coming down this way, so there's 2 of them that add together to create that. So I'm seeing aliasing, and that's expected because this signal is not a purely band-limited signal. Now, if I increased my sampling rate, I would see less aliasing here. In fact, I'd see these things swooping down faster, right? So I would encourage you, I'll post this code, I would encourage you to run this with different sampling rates picked so that you can see the effect at each of these stages. Okay, moving on at the next point. So now we've got that plot installed there. That's our DTFT sub infinity, and we are seeing some aliasing error. Beautiful, beautiful, beautiful. Well, aliasing error is not beautiful, but the fact that we can see it and kind of figure all this stuff out is actually beautiful. On to the next slide. Now we collect only a finite number of samples, some n, and we know in this case n is going to be 8 for our simple example. And we assume that the signal is equal to 0 everywhere else. So we can actually theoretically compute the DTFT of this. It ends up being a geometric sum. And in the book that we used for signals and systems, it's equation 7.6. I'm sure there's an equation in Proacus and Monolacus. We've done this one already, and you should be able to do it yourself. It's just applying a geometric sum to this finite signal case. And we also know that this thing would be the result if we took our x sub infinity and convolved it with our rectangular windows DTFT. Now, it's a heck of a lot harder to actually figure it out that way than it is to figure it out this way. We can figure it out this way because this is a simple textbook signal that's on our tables essentially. But this is how we interpret what's really going on. How this result gets linked to this result. It's through smearing. So this, if we plot this, we should see some type of smearing here. And as I've pointed out before, most textbooks refer to this smearing as leakage error. Okay, let's move to the next slide. Here's some MATLAB code. And again, I'm just going to evaluate this function that I just found for the theoretical version of the DTFT sub n. Can't really do this in practice. I can only do it because this equation is easily found by theory. So I compute that using the same omega points that I used for my DTFT sub infinity, and I plot it the same way, normalized height-wise by capital T, normalized horizontal-wise, frequency-wise, by pi. So I get my beloved -1 to 1 range. I do some labeling and so forth, and I also plot. Well, here I'm plotting the infinity, and then I'm also plotting the DTFT sub n. So this result I calculated on a previous page. This is the result that I calculated right up here. I make the default color. Oh, there goes my dog in the background. Probably somebody walking along the road, and she's getting all excited about that. I plot with the default color, blue, and here I plot with magenta. And so let's look. Remember, we saw the effect of smearing, main lobe issues, side lobe issues, and we can see that on this plot. Look at the blue curve. That's our DTFT sub infinity. And on the magenta curve, we see that it's a little bit wider. That's the main lobe effect. And we see these ripples out here. That's the side lobe rippling effect. So we're seeing both of these effects in this example, and it's great. I don't know if you've noticed, but I'm particularly proud of this little example that I've constructed here. Okay, so that's plotting. And where do we put plot? Well, we put it right down here. So that is the DTFT sub n. So let's recap. We have our CTFT, which we saw makes sense. We've got it plotted on our kilohertz plot. We see that, remember, FS is our is 30 kilohertz. FS over 2 is 15. So remember, FS over 2 is the folding spot. So all of this stuff ends up folding back in to create aliasing, and we're seeing the effect of that aliasing. And now we're seeing the effect of the smearing. We're seeing a broadened main lobe, and we're seeing ripples. So a broadened spike due to the main lobe smearing, and we're seeing ripples elsewhere due to side lobe smearing or side lobe interference. Now, none of this is anything that we could ever do inside a real signal processor. Again, I've said this many times, I'll say it again. We can get these three results. I'm going to go shut that door. I'll be right back. I'm sure you can still hear the dog there. We can get these three results only because we've taken a very simplistic example that we can compute all these things for. But it tells us the story. I'll move on. Now, finally, we are getting to what we can actually do inside our computer. We collect n samples, and we compute a DFT, and we get n DFT points. Well, we might get more if we do zero padding, but we're not going to do zero padding right away. But zero padding tells us that if we did do zero padding, we would just be evaluating more finely spaced points on our DTFT sub n. So what DTFT, or what the DFT theory tells us, is that we're going to get points on the smeared DTFT. So that magenta curve that we just saw, that's the thing that we're going to get points on. So if we actually literally compute the DFT and then we properly scale it with the capital T to make it fit on everything, to be able to be compared to the CTFT. If we were only comparing DFTs to DTFTs, we wouldn't need the capital T, but we're going to keep the capital T there so that we can compare it back to our CTFT. So there's those blue circles that represent the DFT points. I could have plotted them as a stem plot, but I left the stems off. Okay, so that shows what we can actually compute. And if you go back to at the very beginning of this example, I said, collect 8 samples, compute things, here's a stem plot. What is it? Well, there it is. There's what it is. And notice that we're not seeing those ripples. And we're hardly even seeing, we don't see the sides of the main lobe either. That's because we haven't done any zero padding. If we did do zero padding, suppose we collected these 8 samples and then we tacked 8 more zeros on to the end. We're now doubling the length of our FFT processing, which means we would be cutting the spacing in half. Let's see if I can do this here. I would then be getting points halfway in between here. I'm not doing a very good job here. I'd be getting these points, and I'd get one more right there. And so I would be getting a better view of this. I would start seeing some of those ups and down ripples that are there because of the leakage. Now, you might argue, well, yeah, but look, in this case, leaving out those ripples actually gives me something closer to the real one. Well, that's just luck for this one. I would not count on that for any kind of real-world case. We want to see what's there, because we want to see if we have significant leakage error and things like that. So if we could make this grid as fine as we want, the points will always lie on this magenta curve. They will always lie on the DTFT sub n, no matter how much we zero pad. So zero padding can't fix the smearing error due to collecting a small number of samples. Don't let anybody ever tell you that it can. There are some people out there who don't really know what they're talking about and will try to tell you that zero padding fixes that. It doesn't. Okay, so let's put all of this together. This now shows all 4 plots, and remember, the only thing that we really can compute and can really see are those blue circles in that final plot that's down in the lower right corner. That's what we can compute. And I'm showing the potential for zero padding here, even though I didn't really do zero padding for this particular figure. But this shows all the underlying stuff that leads to how we get those points. And so this really explains what all the errors are, how they interrelate. We've got aliasing error, we've got smearing error, and we've got grid error. And we know how to fix all of those to some degree. Aliasing error we fix by sampling faster. Smearing error we fix by collecting more data, although we'll soon see that we can fix it by using different shapes of windows. Grid error we fix by zero padding. And all of that can be seen here in this beautiful little example. And hopefully this kind of lays it all out for you to see how it all works. And I think that's it. Yep, that's the last slide. So I'll see you in the next set of notes.